If you wanted to find the fundamental blueprint for a revolutionary new material, I mean, the actual operating instructions for a quantum engine, you wouldn't just look at the surface.
No, you wouldn't.
You'd have to find that hidden data crystal, the Star Wars holocron that spells out the deepest rules of its existence.
And that, in a nutshell, is the mission we're unpacking today. A team of physicists has performed, well, a truly unprecedented deep dive into this fascinating material.
And what's it called?
It's called Magic Angle Twisted Trilayer Graphene, or MATTG for short.
Welcome to the deep dive, where we take complex research, the kind that makes you feel like you need a chemistry degree just to read the abstract, and we distill it down.
Down into the core nuggets of knowledge you need to be well-informed.
And today, our focus is intense. We're trying to identify the nature of superconductivity in this highly unconventional, two-dimensional material.
Our sources for this revolve around a really landmark paper. It was published in the journal Science.
And the title?
The title is Experimental Evidence for Nodal Superconducting Gap in Moiré Graphene.
This research really stands out. I mean, they weren't just observing a phenomenon. They were actively trying to prove how the electrons paired up to create that zero-resistance state.
And that required, frankly, extraordinary experimental ingenuity.
We should definitely give a shout-out to the team responsible.
We absolutely need to. The key contributors included Jongmin Park and Shuin Sun from MIT and Princeton, and also Kenji Watanabe and Takashi Taniguchi from the National Institute for Material Science in Japan. The work was led by a real pioneer in the field, Pablo Girillo Herrero at MIT.
And their goal was to pinpoint the specific pairing symmetry of the electrons.
Right.
Which is kind of like the foundational instruction set, maybe the core operating system of the superconductor.
That's a perfect analogy. And understanding the symmetry, it's not just some academic fluff.
No, it has real-world implications.
Huge implications. It's critical because it dictates how the material will behave under stress like heat or magnetic fields and what future tech we might build with it. Okay, let's unpack this quantum sandwich.
Let's start with the material itself, MATTG. So we all pretty much know graphene is a single sheet of carbon atoms.
A honeycomb lattice, just one atom thick, the ultimate two-dimensional material.
Now, you stack 3 of those sheets together, but the magic isn't just the layering, is it?
No, it's all in the twist. The top and bottom layers are twisted relative to that middle layer by a tiny, very specific alternating angle.
How tiny are we talking?
Around 1.56 degrees, we call this the magic angle.
And that precise infinitesimal twist creates a super pattern, right? A huge geometric structure called a moiré pattern.
Exactly. You see the same effect when 2 window screens slightly overlap and create that, that dizzying optical illusion.
But this is happening at the atomic scale.
Exactly. And for the electrons, this moiré pattern is a total game changer. It forces them into these flat electronic energy bands where they move really slowly and interact very strongly with one another.
And when they interact that strongly, they start to cooperate.
They do. They lead to these fascinating collective behaviors, including superconductivity, where electricity just flows with zero resistance.
But the challenge they faced was a classic one in this field. In these strongly interacting systems, it's just incredibly difficult to tell the difference between different energy states.
Right. Specifically, which energy gap, which you can think of as the protective shield that keeps the electron pairs stable, is the true superconducting gap.
Previous experiments, they really struggled with this, didn't they?
They did. They faced a dilemma because they needed 2 types of measurements. Electrical transport, which is, measuring the zero resistance.
Right, the actual superconductivity.
And tunneling spectroscopy, which measures the density of electron states, or DOS.
So if they measured those 2 things on 2 separate, tiny flakes of graphene, even if the flakes looked identical, what was the problem?
The problem is that the magic angle is sensitive down to 1/10 of a degree. So any slight difference in the twist angle or even a tiny defect on one flake versus the other,
it throws the whole thing off.
It meant the data wouldn't correlate perfectly. You couldn't definitively say the energy gap we see here is what causes the zero resistance we measure over there. It created this fundamental ambiguity.
So they had to solve the device problem first. And this is where the innovation of the Team Park Sun and Girillo Herrero, it really shines.
Oh, absolutely. They needed to find a way to perform the, let's say, the X-ray and the speedometer reading at the exact same time on the exact same spot.
How did they even do that?
They engineered this highly specialized device structure made entirely out of what are called van der Waals, or VDW, materials.
Those are materials held together by really weak forces, right? So you can stack them like atomic scale paper.
You're talking next-level quantum Lego here.
Ah, I like that. Quantum Lego.
It is. They stacked 2 layers of NTG, a top one and a bottom one, and they sandwiched a thin insulating wall of hexagonal boron nitride, or HBN, right between them. This is the crucial part.
So the stack is essentially a vertical tunnel, 2 separate superconducting layers, but they're close enough that electrons can tunnel through that HBN wall.
Yes, when you apply a small voltage, that's the bias. By applying a DC bias voltage across that barrier, they could measure 2 things at once.
Okay, what were they?
First, the density of electron states, vertically, through the tunnel. And second, they could simultaneously measure the electrical resistance, the transport, laterally within the ATG layers themselves.
So that simultaneous measurement just eliminates the ambiguity entirely.
Completely. They established a direct, undeniable link between the energy states they measured vertically and the zero resistance state they measured horizontally, all in the same spot. That's the real experimental breakthrough. They built the perfect diagnostic tool.
And once they built that tool,
they immediately used it to uncover the secrets hidden inside that quantum blueprint.
And here's where it gets really interesting. When they used this V-tunnel technique V for the voltage, I'm guessing they didn't just find one energy gap.
No, they found the coexistence of 2 distinct V-shaped energy gaps in their data. It was like finding the main shield generator and a backup shield generator running at the same time.
So how do you tell them apart? How do you know which is which?
You need a scientific stress test. So they tracked how both of these gaps responded to changes in temperature and magnetic fields.
Let's talk about the fragile one first, the low energy gap. They labeled it delta SKO.
That one behaved exactly as a true superconducting gap should. It was incredibly sensitive.
How so?
This sharp, low-energy gap, it rapidly filled up and just vanished right around the material's superconducting critical temperature, or T-Carely.
And that was what, about 1 Kelvin?
Very cold.
Very cold, but not unexpected. The moment the material lost its perfect zero-resistant state, poof, this gap was gone.
That direct, rapid correlation confirms it as the true superconducting engine. Without a doubt. They measured this delta to be about 0.159 millielectron volts near optimal doping. It's a tiny but powerful energy shield.
Okay, so now compare that to the second one, the higher energy gap, delta Hg.
This gap was broader, shallower, and much, much tougher.
They're tough.
Well, when they cranked up the temperature past T epicenter, the low energy gap disappeared, but the delta Hg barely even flinched.
Seriously?
It stubbornly persisted up to around 8 Kelvin. That's 8 times higher than the temperature needed to kill the actual superconductivity.
So this high energy gap is sticking around long after the party's over.
It is. And the difference was also stark with magnetic fields. The fragile superconducting gap, delta S, it was just annihilated by a tiny perpendicular magnetic field around 0.04 Tesla.
Wait, hold on. 0.04 Tesla, that sounds incredibly small. For context, that's maybe 800 times stronger than Earth's magnetic field, but still tiny for engineering.
That's a great point.
So if the true superconducting gap is that fragile, what does that mean for using it in real-world devices that, might encounter stray magnetic fields?
That's exactly the right question to ask. It suggests that while the pairing is super interesting, this particular state is mechanically fragile. But the contrast with the other gap is just dramatic.
So the tougher gap, the delta Hg, what happened to it?
It was largely unaffected by that small field. It survived even up to 1 Tesla.
So the small sensitive gap is the one doing the work, causing the zero resistance flow. But the big hardy gap, delta Hg, just sort of hangs around like a ghost.
That's a great way to put it. And the authors conclude this higher energy gap is not the superconducting gap. They suggest it might be a pseudogap.
And that term is significant, right? Because we've heard it in other contexts.
Very significant. It's similar to what's observed in high-temperature cuprate superconductors, the materials that work above liquid nitrogen temperatures.
Why does that connection matter so much?
Well, in the cuprates, the pseudogap is often thought to be caused by preformed pairs of electrons. These are electrons that have already decided to partner up, but they haven't achieved the final quantum phase coherence.
The synchronized marching.
The synchronized marching, exactly, that officially makes the material superconducting. So finding this pseudo-gap in MTTG suggests that moiré graphene shares fundamental physics with the most complex, high-temperature superconductors we know.
So this elevates MPTG from just a cool curiosity to a material that's directly relevant to solving those big high-temperature mysteries.
It really does. That distinction, the delicate true gap versus the robust pseudogap, it clarifies years of confusing data. And with that clarity, they could finally move on to the biggest question of all.
What is the exact nature of the pairing symmetry?
This is the moment they figured out if MTTG is a conventional superconductor, the textbook kind, or something much more exotic and unconventional.
Let's use that energy shield analogy again. If superconductivity is this shield protecting the electron pairs, what are the two main types?
Okay, so conventional or swave superconductivity is like a perfect, smooth, spherical energy barrier. The gap is the same no matter which direction a disturbance tries to approach from. It's maximally robust.
Like Captain America's shield, nothing gets through.
Right. But unconventional or nodal superconductivity.
What's that like?
That's where the shield has specific directional nodes or holes where the energy gap just vanishes entirely. Think of it like a defense shield with specific blind spots. Quasi-particles can leak through these nodes much more easily.
So if you can prove those blind spots exist, you prove the material is unconventional.
You got it. And the MIT and NIMS teams gathered three highly technical but highly compelling pieces of evidence to prove that MATG is in that unconventional nodal camp.
Okay, let's break them down. Evidence number 1.
Temperature-filling behavior. They track something called the zero bias conductance. To keep it simple, that's just a measure of how easily electrons can move when you apply almost no pushing force.
And they looked at how that measure increased as they warmed the material up towards its breaking point, towards Titakarine.
Exactly. Now, in a conventional system, that perfect bubble shield, you wouldn't see many excitations until you get really close to Titakarine and the whole shield just collapses.
But a nodal system has those holes.
It has the holes, so the minute you add even a tiny bit of heat energy, those quasi-particles can immediately start leaking out through the nodes.
And is that what the data showed?
That's precisely what they found. The zero bias conductance immediately rises linearly with increasing temperature, well before the transition temperature is even reached. That linear rise is the telltale signature of a nodal order parameter.
Wow. So that's already linking this graphene system directly to the physics of high-temperature superconductors.
It is. But the second piece of evidence, the one you called the wow fact earlier, this is the definitive proof. The Volovic effect.
This sounds cool.
It's truly beautiful physics. The team applied a small perpendicular magnetic field, be it Parton, and tracked the increase in that zero bias conductance again. They were looking for a very specific, mathematically precise relationship.
A relationship that was predicted decades ago, right? Not something they just came up with.
Exactly. And they found that the zero bias conductance exhibited a square root dependence on Bayer-Perp. It increased proportional to the square root of the magnetic field strength.
A square root dependence. That sounds incredibly specific. Why is that mathematical relationship the smoking gun that proves the pairing is nodal?
Because in superconductors with nodes, applying that perpendicular magnetic field creates these quantum vortices, tiny whirlpools of current. And those vortices interact specifically with the existing nodes in the energy gap.
Okay.
And theoretical models, including ones from Volovic, showed that only a system with a nodal order parameter, a system with those pinholes, will generate a change in its density of states that follows that exact square root relationship. It is the absolute gold standard for confirmation.
That is just amazing. They're using a mathematical prediction from decades-old theoretical physics to confirm the quantum nature of a material synthesized just a few years ago.
It is. That finding is what fundamentally defines MATG as an unconventional superconductor.
And there was a third piece of evidence?
There was, also involving magnetic fields. Evidence 3 involved the in-plane magnetic field, parallel. So they ran a magnetic field parallel to the sheets of graphene.
And what happened?
The zero bias tunneling conductance immediately started to increase, even at very small fields, before it eventually saturated around 2 Tesla.
Why is that immediate response to a parallel field so important?
Well, in conventional swave superconductors, the energy gap is usually pretty robust against an in-plane field until the field gets strong enough to physically rip the electron pairs apart.
But not in a nodal system.
Right. In a nodal system, the applied field interacts with the orbital motion of the electrons, and because the nodes are already there, that interaction immediately and efficiently generates more of those quasi-particles. This quick response just further cemented the case for a nodal order parameter.
Okay, this research has completely rewritten the quantum instruction manual for MPATGG. Let's zoom back out and summarize what this deep dive has really taught us.
For me, the first key takeaway is the methodology itself, that simultaneous transport and tunneling spectroscopy method leveraging these VDW materials. It solved a major problem in the field.
So the tool they built is almost as important as what they found with it.
I think so. This framework, developed by Park, Sun, Chirilla Herrero, and the whole team, is now a template for future research.
Okay, takeaway number 2.
Second, the research confirmed the dual nature of these energy gaps. We now know that the true, delicate superconducting engine is that low energy gap, delta ST, and that it coexists with a much hardier, higher energy pseudogap, the delta Hg.
And that directly connects moiré graphene physics to the really challenging high-temperature realm of the cuprate superconductors.
It does. And the third, and I'd say most profound finding, is the nature of the superconducting pairing itself. It is nodal.
Confirmed by the temperature behavior, and most crucially by that beautiful mathematical signature of the Volovic effect, that square root dependence on the magnetic field.
Exactly. By confirming the nodal pairing symmetry, MATCG joins this really exclusive club of unconventional superconductors.
Which tells us the material is highly sensitive, sure, but its very nature might mean it could operate under different conditions than conventional systems.
For sure. And this experimental framework is so versatile. It can now be used to precisely study other sensitive 2D moiré materials, like twisted transition metal diachologenides. It gives us the tool we need to start cracking the code on all these correlated quantum phases.
So if we can precisely engineer these energy gaps, if we can control this pairing symmetry in these new 2D quantum materials, if we can deliberately introduce those specific nodal blind spots, what kind of breakthrough in, say, fault-tolerant quantum computation or zero-loss energy transmission might be just one tiny magic twist angle away?
That's the question, isn't it?
It is, and that's the question we'll leave you with to consider.
Thank you for joining us for this deep dive into the world of quantum materials and unconventional superconductivity.
If you love learning something new today, hit that subscribe button to catch our next exploration.